Great. Thanks so much, Bruce, for your invitation. It's a pleasure to be here on a topic that is near and dear to my heart and one that is very much at the center of the efforts that McKinsey has been doing in the space, a clear priority for us. I thought it would be interesting to give a practical example of where the rubber hits the road for companies that have to make decisions around climate impacts. And while we've done work in a whole host of industries, we thought it would be interesting to actually give an example of an electric production and distribution utility that would highlight some of these key themes and issues that we see. So essentially, this utility in the Great Lakes region asked us three questions. One was about their physical climate risk exposures over a horizon of 2030. The second one is, okay, what is going to happen at the same time from a transition perspective? So transition means electrification, electrification means demand. And so what is going to happen to our demand to the extent that the transition is happening? And then the third question is, what do we do about it? How should we think about our capital planning and the actions that we take to respond to this? So in any such effort, the first step is to identify the risks or the hazards actually that are relevant. So, you know, the list of acute and chronic hazards, and it's a matter of first starting by looking at their frequency and severity and seeing what might be applicable. So this is an example of the heat map that you see in this case. On one dimension, you have the impact or severity. On another one, you have the frequency. And so you recognize the hazards like storms, extreme heat, flooding, etc. It's interesting, the same hazard can manifest itself in two ways for an electric utility. So higher average temperatures mean that you have more cooling demand, and it manifests itself on the one hand as an increased risk. And actually the same higher average temperature means that your heating demand in winter go down. So for any given company, you have to translate those hazards into what they mean. Now, in this case, as we looked at what it meant for this specific utility in this specific location, and I can emphasize that enough that climate is the revenge of maps over spreadsheets. It's always super local. It is according to a fine grid, etc. So in this specific location, three risks emerged. One was extreme heat. The other one was storms and flooding. Now, when we looked more closely at it, flooding was deprioritized because they had only a limited number of substations that were really exposed to flooding. So flooding was increasing for the region, but was not increasing meaningfully for them. And of course, this is, as I said, a local view, and it's a view up to a horizon of 2030. Obviously, if you project forward, you know, this picture is going to be different. Now, so I said earlier that, you know, you had this extreme heat and storms. Storms themselves come in three flavors. There is thunderstorms, there are year-round storms, there is freezing rain and ice, and as I said, there was also heat, which means that you need to have more cooling loads. And so now what needed to be done is to have a granular view of what happened. So we use the proprietary utility data together with demographic information, together with obviously fairly fine-grained climate models to be able, and then on top of the climate models, the hazard models, to be able to say, okay, for instance, for thunderstorms, you know, there will be more on the western region, less on the eastern region. For year-round storms and freezing and ice, we developed specific tailored models for this case. And it's interesting, you look on the chart and cooling loads, again, seem to be heavy here, but in reality, when you look at it, they don't lead to as many outages and the type of issues that many of these utilities are worried about. So it allows to have both a view of where the hazards are, how they affect the network, and what really matters or not in terms of managing it. Now, when, for instance, you take these different storm hazards and you create a combined map that sort of looks at the total storm-driven outages, you see the areas where this is going to be, so the darkest areas, are the areas that are going to be differentially affected. And so what you find there is that while, on average, during this period, this hazard increases 10 to 15%, there are subregions where it's 30%. And this is yet another one of the very common themes, I'm sure, throughout the day. You've heard people talk about averages, but climate is really about sort of all of the parts of the distribution, and particularly the extremes. And if you want to take action, you need to understand that distribution and those extremes. So this allows to say we are going to target specifically that those areas where there is that 30% increase. And by doing the right things, we can bring down up to 60% the likelihood of these outages. So so if you understand the risk, now it comes in the realm of what we do about it. And so this chart represents, so the first bar represents the amount of outages that they have today. By the way, utilities typically have a reliability of 99.9, et cetera. So it's sort of, although there is a number of outages that affect people, in general, they're quite operating at a very high level of reliability. So we could project based on these hazards how much more there would be by way of outages because of these various loads that we described. And that's represented by the pink number. And then what is interesting is what can you do about it and how much does it cost? And if you look at it, first of all, quite interesting that the first two levers, digital-enabled vegetation trimming and digital-enabled asset inspections and repairs, these in itself are hugely driven by data and analytics and geospatial, and there are all these solutions that are now on the market that allow you to have 3D models and sort of truly understand and intervene for things that historically were done very intuitively. And you look at these and say, we have indexed it here, and you see, okay, so if the first one, which is digital-enabled vegetation trimming, is a unit of 1, you can see how these increase as you get more and more physical and more intrusive. So overhead hardening, so the overhead line hardening is 1.8, but by the time you get to undergrounding or additional undergrounding, it is 5 times more expensive. And so this raises the question of what our target level should be and how much it costs. And why it is relevant, and I think it's a very meaningful thing in the climate space, is that you have to make, in adaptation, trade-offs between cost, and that is affordability, and level of protection. And you need to be very thoughtful about how you do this, because obviously both are targets. You want to keep energy prices low and affordable. At the same time, you need to do a hardening here of assets that is relevant. And so this highlights one of the issues that people on the ground see quite regularly. Now, the second question was, what happens to our demand as we electrify more? And the traditional thing that you will find in many utilities is that they have projections like you see on the left-hand side. Essentially, they say, okay, so if there are more heat pumps in the territory, this is going to impact our loads in such and such fashion, and we have a projection between now and 2050. But what we did in this effort is, again, to say, okay, let's get quite granular here. Let's look at all the demographic and other information that the utility has on others, and let's project area by area what the adoption of these different new technologies is going to be, therefore the demand on electricity. And you see that very different pictures emerge. So again, the darkest color is the highest level of increase in circuit loads. And you can see that there are archetypes that emerge. So you have a suburban circuit, which is a very affluent area. There are high levels of expected technology adoption. There will be high demand, and that's one type. And then you have the industrial outskirts where things are going to move much more slowly, and therefore your loads are going to evolve differentially, and you will need to prepare from a perspective of additional demand quite differently as well. And then it's very interesting how certain things are unintuitive. By the way, this is another theme in climate in general. Quite often, second-order effects can either negate or vastly amplify first-order. It's not as simple as, you get the bulk of it with the first order, and then these are corrections. So, for instance, the thing which is interesting is that the projection here was that although it's becoming warmer, the summer loads are unlikely to change when you do the detailed modeling that much. But the winter loads, because of the adoption of heat pumps, and the projected are actually going to increase. This would have been counterintuitive if you just looked at it from outside, but if you actually model it, you see that. By the way, one thing I should have said, obviously, because of the latency of the Earth's climate system, these things that we're projecting with a horizon of 2030 are almost independent of scenario, because the next 10 years are largely baked. So it is going to be even not that much of a question of scenario. There's a high degree of likelihood around these things. But the counterintuitive nature of some of these and the implication it has for how we're going to deal with it. Another thing that I wanted to show is, how things are going to evolve. So utilities are worrying about 2 times 2 things. So it's about winter or summer peaking circuit, and then to what extent you're at the risk of overload. And so if you look at the picture of now, which you have a winter peaking circuit at the risk of overload, which is a lot, and some winter peaking, and you project to 2050, and you see that with this evolution, the picture is going to be very different. You will find more and more winter peaking circuit at the risk of overload, and more summer ones, and the others are going to sort of become less relevant. So what do we do with all of these things? And what was the impact of doing this type of thing? This allows the utility to have a much clearer grasp of what their resiliency and capital needs are. It allows also to target very specifically where outages might occur and reduce them at a lower cost. As I said earlier, it also enables a discussion around risk appetite and how far we're going to go. And the differences are huge. So, for instance, the investment needs from one circuit to the other, we discovered, could be as much as 8 times different. And again, this is a much more precise capital planning. Now, this was a picture as of a certain point. All of these things are evolving. So as utilities think about these things, this is not something that is, a one-time exercise. Actually, the most advanced ones are building capabilities for doing things on a regular basis. And I think this discipline of thinking is going to be increasingly adopted across the board. Thank you so much for your attention, and thanks again for having me here.